Introduction to PyArrow. PyArrow is a Python library for working with Apache Arrow data. It allows fast, zero-copy data exchange between different computing tools. PyArrow is useful for working with big tabular datasets efficiently. Real-world uses, accelerating data loading, reading Parquet files, sharing data between Python and other languages, powering machine learning, and more. PyArrow makes big data workflows faster and more memory efficient. Running the cell now. We ignore warnings to keep the output clean and easy to read. We import system in case we need to check system or Python details. This comment explains how to install PyArrow on Windows. This comment shows the pip command used to install PyArrow. Now we import the main PyArrow module for working with Arrow data. Here we import the Feather submodule for fast columnar file storage. Here we import the Parquet submodule for efficient analytics file formats. Running the cell now. This code sets up the environment to use PyArrow by importing its core modules and related submodules for Feather and Parquet file handling. Although there's no direct output, notice that these imports are essential to enable fast, zero-copy data operations on big tabular datasets, which is the foundational step for all subsequent PyArrow functionalities covered in this lesson. What are arrow arrays and tables? PyArrow has two main data types, arrays and tables. An arrow array is like a column of data with a specific type. An arrow table is similar to a table in SQL or a data frame in Pandas. Arrow tables are made from multiple arrow arrays. Arrow data is stored in a fast, columnar format. Running the cell now. Let us create an arrow array from a list of integers. We call PyArrow to convert a Python list to an arrow array. Let us print the arrow array. Running the cell now. This output shows a simple arrow array with 5 integer values, demonstrating how PyArrow represents a single column of data. Notice the values are displayed in a list-like structure, highlighting the array's shape as a one-dimensional sequence. This reinforces the concept that arrow arrays hold typed column data, the building blocks for creating arrow tables. You can create arrow arrays with other data types, like float. Here is an arrow array with floating point numbers. Let us print it. Let us also create an arrow array with strings. Let us print the string arrow array. Running the cell now. Here we see 2 arrow arrays printed, one holds floating point numbers, and the other holds strings. Notice how each array is a simple, typed sequence of values, illustrating that arrow arrays represent single columns of data with a consistent type. This output highlights the core idea that arrow arrays store data efficiently and type specifically, laying the foundation for building arrow tables. Now let us build an arrow table from 2 arrow arrays. We pass a dictionary with column names to PyTable. Let us print the arrow table. Running the cell now. This output shows an arrow table composed of 2 columns, numbers of type double and letters of type string. Notice each column holds an arrow array, where are numbers it contains numeric values and the letters contain strings, reflecting how tables organize multiple typed columns together. This demonstrates the core idea that arrow tables are collections of arrow arrays combined into a structured data set. Beginner, accessing data. You can select columns and rows in arrow tables. PyArrow allows you to easily inspect and slice tables. Running the cell now. Let us access the numbers column from the table by name. We print the numbers column. Running the cell now. This output shows the values from the numbers column in the arrow table, displayed as a list of floats and integers. Notice how the code selects and prints just this column, demonstrating how you can access specific data within the table. This helps you focus on individual columns when inspecting or manipulating your data. We can access the first 2 rows of the table using the slice method. Let us print the first 2 rows. Running the cell now. Here, the code uses slice notation to select the first two rows from the table. Notice how the output shows only the values for these rows in each column, preserving the original column names and data types. This demonstrates how PyArrow lets you quickly access and inspect specific parts of a table, a key step in managing and exploring data. We can easily convert an Arrow table to a Pandas data frame. First, we import Pandas as PD. We use the to_pandas method to convert the table. Let us print the data frame to see the result. Running the cell now. This output shows a simple table with two columns, numbers, and letters, converted from an Arrow table to a Pandas data frame. Notice how each row is indexed from 0, making it easy to access specific rows or subsets of the data. This conversion highlights how PyArrow enables seamless inspection and manipulation of Arrow tables using familiar Pandas operations. Intermediate, reading and writing Arrow files. PyArrow can save data to disk and load it back quickly. You can save tables as Arrow IPC, Feather files or as Parquet files. Running the cell now. Let us write our Arrow table to a Feather file on disk. We use parfeather.write_feather to save the table. Print a message when finished saving. Running the cell now. This output confirms that the PyArrow table has been successfully saved to a Feather file named my_table.feather. In this lesson section, the key takeaway is how easy it is to write data to disk using the Feather format, enabling fast and efficient storage and later retrieval without losing the table structure or metadata. Now let us read the same table back from the Feather file. We use parfeather.read_feather to load the file. Let us print the loaded table. Running the cell now. Here, we successfully read the data back from a Feather file into a PyArrow table, preserving the original structure. Notice the table retains both columns, numbers with float values and letters with strings, showing how Feather files efficiently store and restore mixed-type data without loss. This confirms the ease and speed of using Arrow IPC format for saving and loading tables in real-world workflows. Let us try saving the table as a Parquet file. We use pq.write_table to save it to disk. Let us print a message after saving. Running the cell now. This output confirms that the table was successfully saved to a Parquet file, demonstrating PyArrow's ability to efficiently write data to disk. Notice there's no error, so you can trust Parquet for fast, reliable storage and later reading of your data in the same Arrow format. Let us load the table back from the Parquet file. We use pq.read_table to open the Parquet file. Let us print the table we just loaded. Running the cell now. This output shows that the Parquet file was successfully read back into a PyArrow table with two columns, numbers, double, and letters, string. Notice the data retains its original structure and types, demonstrating that PyArrow preserves data integrity when saving and loading Arrow tables. This reinforces the lesson's point about efficient, lossless disk storage using Parquet files. Intermediate, Arrow schema and data types. Arrow arrays and tables have strong, explicit data types. Table schemas help ensure data consistency when sharing or saving data. Running the cell now. Let us check the schema of our Arrow table. We print the schema, which shows columns and data types. Running the cell now. This output shows the schema of the Arrow table, listing each column name along with its explicit data type, numbers as double and letters as string. This confirms the strong typing that Arrow enforces, which is crucial for data consistency and reliability when processing or sharing tables. Noticing these types helps ensure your data matches expectations before further analysis. You can create Arrow arrays with missing values by using none. Here is an example. Print the array with null values. Running the cell now. This output shows an arrow array containing integer values with an explicit null entry, demonstrating how Arrow handles missing data using its strong, explicit data types. Notice that none in Python is represented as null in the arrow array, emphasizing the schema's ability to represent nullability clearly and consistently. This is important for maintaining data integrity when working with incomplete datasets. Advanced, chunked arrays and large datasets. Arrow tables can store data in chunks, useful for big data. You can combine arrays or append new data efficiently. Chunked array lets you process data without loading everything at once. Running the cell now. Let us create a chunked array from two separate arrow arrays. We use par_chunked_array and parse lists or arrays. Print the entire chunked array. Let us also print how many chunks are in this array. Running the cell now. This output shows a chunked array composed of two separate arrow arrays, each holding a small list of integers. Notice the structure retains two distinct chunks, which you can verify with num_chunks, reflecting how Arrow handles large datasets by breaking data into manageable parts. This emphasizes how chunked arrays allow efficient data processing without loading everything into memory at once. You can append new rows to a table by combining tables with concat_tables. Here is a first table T1. Here is a second table T2. We combine them using par_concat_tables. Let us print the combined table. Running the cell now. This output shows the combined arrow table after appending rows from two smaller tables. Notice the column that is stored as a chunked array with two chunks, reflecting the original table's separate arrays. This highlights how Arrow efficiently handles large datasets by keeping data in chunks rather than merging into one continuous array. Advanced, zero-copy data sharing. Arrow format allows multiple languages and libraries to share data without copying. You can parse arrow arrays from Numpy or Pandas efficiently using zero-copy. Running the cell now. Let us see how to convert a Numpy array to an arrow array. First, we import Numpy. Here is a Numpy array. We use PyArrow to convert it to an arrow array without copying data. Print the arrow array. Running the cell now. This output shows the arrow array created directly from the Numpy array without copying data, preserving the original values and structure. Notice how the elements remain identical and in order, demonstrating efficient zero-copy sharing between Numpy and Arrow for seamless interoperability. This confirms the intent of parsing data in Arrow format to avoid costly duplication. You can also convert an arrow array back to a Numpy array. Here we use the to_numpy method. Print the Numpy array. Running the cell now. Here, the output, 10, 20, 30, shows that the arrow array has been converted back to a Numpy array without copying the data. Notice how the values remain intact and the array shape is preserved, which demonstrates efficient zero-copy sharing between Arrow and Numpy as highlighted in this advanced lesson. Error handling example. PyArrow will raise errors if you use unsupported data. Let us see what happens with a bad data type. Running the cell now. Let us create an arrow array from a nested list. This will cause an error. We use a try block to catch exceptions. Try to build the array. Catch any exception. Print the error message. Running the cell now. Here, the code attempts to create a PyArrow array from nested lists, which is not supported by PyArrow's data model. As a result, an error is raised and caught in the try except block, preventing a crash but showing that nested lists cannot be directly converted. This highlights the importance of understanding data types that PyArrow can handle to avoid runtime errors. Here is a helper function to check if data can be converted to arrow array. Define the function safe_arrow_array with one parameter. Try to make the arrow array. If successful, print the array. If it fails, catch the error and print a message. Test with a good data list. Test with a list of dicts which is not directly supported. Running the cell now. This output shows that the first list of integers convert smoothly into a PyArrow array, confirming supported data types work as expected. However, the second input, a list of dictionaries, also converts but results in a nested structure with child arrays, highlighting how PyArrow handles more complex types instead of outright failing. This demonstrates the importance of checking data compatibility and understanding the structure PyArrow creates when dealing with unsupported or complex data. Best practices with PyArrow. Prefer Arrow for tabular, column data in big data workflow. Use Arrow arrays and tables for efficient serialization. Use zero-copy interfaces for integration with Numpy and Pandas. Convert data back to Pandas or Numpy only when necessary. Always specify Schema when saving data for reliability. Running the cell now. Here is how to specify a schema for your Arrow table. We create a schema object, listing column names and types. Build a table with the schema specified. Print the table to verify it. Running the cell now. This output shows a PyArrow table explicitly created with a defined schema, specifying column names and types. Notice that the columns ALA and BEAD hold integer and string arrays respectively, illustrating how Arrow enforces and preserves data types for efficient processing. This practice ensures data consistency and optimizes workflows when handling tabular data in big data environments. When dealing with file handles, always close them after reading. Use a context manager with PAR-OS file to open the file in binary mode. Read the table from the opened file. Print the shape of the loaded table. Running the cell now. Here, the code reads a Feather file into a PyArrow table using an OS file handle, emphasizing best practice by closing the file automatically with a context manager. The output shape, 3, 2, confirms the table has 3 rows and 2 columns, illustrating efficient, zero-copy reading of tabular data without converting to Pandas yet. This underscores PyArrow's strength in handling columnar data efficiently in big data workflows. Mini-project, analyze a small dataset. Let us simulate loading, filtering, and saving a dataset using PyArrow. We will 1. Create sample data. 2. Filter rows. 3. Save and load it in Parquet format. Running the cell now. First, let us create sample data as an Arrow table. Create an Arrow array for ID numbers. Create an array for values. Create an array for scores. Build the example Arrow table. Let us print a label. Print the table to see the data. Running the cell now. This output shows the initial PyArrow table we created with 3 columns, ID, value, and score, each containing 5 rows. Notice the data type specified, int64 and double, and how the data is neatly organized in columns, which sets us up for efficient filtering in the next step. This confirms our sample dataset is structured correctly before we proceed to manipulate it. Now let us filter the table for scores over 60. Build a Boolean mask for score greater than 60. Use filter to get only the rows matching the mask. Print a label to explain the filter. Print the filtered table. Running the cell now. This output shows the filtered table containing only rows where the score is greater than 60, reducing the dataset from the original to just 3 rows. Notice the shape and that the key columns, ID, value, and score align correctly, confirming that the filter worked as intended to select higher scoring entries. This demonstrates how PyArrow's filtering can efficiently subset data based on conditions. Now let us save the filtered table as a Parquet file. Write the filtered table to disk. Read it back as an Arrow table. Print a label. Print the reloaded table for confirmation. Running the cell now. This output shows the filtered dataset successfully saved and reloaded from a Parquet file, preserving its structure. Notice the 3 rows with IDs 3, 4, and 5, confirming the filtering step retained only these entries. This demonstrates how PyArrow efficiently handles storage and retrieval of table data without losing any information. YouTube, like and subscribe. If you enjoyed this PyArrow lesson, please like and subscribe for more Python tutorials. Running the cell now. Want more? Comment below if you want a deep dive on PyArrow or data engineering topics. Running the cell now.